So let's welcome Professor Goldberg. Let's give him a applause.
Okay, thank you for the introduction. And yeah, thanks to BIMSA for inviting me to speak. So I will not tell you what ZFC is in this talk. So you're just going to be completely, no, we'll see. We'll see how this goes. Okay, so what I'm going to talk about is first large cardinal axioms. Is it okay? It's definitely on. I can get it. Okay. Do I sound better? Okay. No, but that's fine. I don't need the mic. Okay, so I'll talk about large cardinal axioms. So maybe this will sort of explain what ZFC is. Maybe. It's a way of extending the foundations of math to stronger theories that can decide more statements. And it's especially tied up with the question of the consistency of foundational theories in math. Okay, so that's maybe the most important thing I'll talk about. And then I'll talk about sort of the edge cases of these large cardinal hypotheses, sort of the frontier of research there and the strongest axioms known to humanity. And then I'll talk about sort of how we understand these large cardinals now and the connections to other strong theories that have been looked at since the 1980s, which are much better understood. And these are determinacy theories. So they come sort of from analysis and descriptive set theory dating back to like the 1920s. Okay, so the background. I have a lot of background here, but I won't list the axioms of set theory. Okay, so how do you establish that a formal theory, so a collection of axioms, is consistent? That, I think, is the most fundamental question in foundations, because we'd like to know whether the theories that we work with are actually consistent, meaning that they don't prove contradictions. Okay, so how do you know, for example, the axioms of number theory, the axioms of set theory are consistent? And the problem with this question is that it's sort of impossible to establish that a formal theory is consistent, at least mathematically, because to really do this in a non-trivial way, you would have to establish it from some weaker theory that you're more confident in. And it's just impossible to do that. Okay, if you take any collection of axioms, there's no way for those axioms to prove their own consistency, or any weaker set of axioms to prove their consistency. Okay, so there's almost no way to establish the consistency of a formal theory mathematically. Okay. On the theory, T? For Gödel's theorem? Mm-hmm. Oh, that they're minimal. Often, yeah. But I mean, for example, the axioms of set theory basically have that form. You can't delete any of the axioms. Keep the same system. But this is different. The question of consistency is whether the axioms are sort of trivialized, whether they prove both the theorem and the negation of the theorem, which would make them pretty useless. Okay, so sort of impossible to mathematically establish that a theory is consistent. So it makes it a different kind of problem from basically anything else you face in math, even though it's a very concrete question. It's just you have some finite collection of axioms, say, and you want to know whether there's some derivation of a contradiction from those axioms. It's just not possible to say in general. But the kind of amazing thing is that the foundations of math have managed to answer this question, at least to the best extent we could hope, given this theorem. Okay, so let's start with the simplest possible case. So how do you know that the axioms of number theory are consistent? Okay, so these are just the axioms that sort of characterize the structure of the natural numbers with plus and times. Okay, so they say things like, you know, for every number, there's a number one bigger than it. I don't know, they characterize multiplication in terms of addition, things like that. So the way we know, I don't know, this is sort of the dogmatic answer. The way we know that these axioms are consistent is that they have a model. There's a structure in which all of the axioms are true. Okay, so there can't be a derivation of an inconsistency, right? There can't be a statement that follows from the axioms and whose negation follows from the axioms, because then that statement and its negation would both be true statements about the natural numbers, and that's just impossible. Okay, so there's a proof that the axioms of arithmetic or number theory are consistent. But obviously that proof is sort of circular. I mean, by Gödel's theorem, that proof cannot possibly have been carried out within arithmetic. I moved to a stronger system in order to prove the consistency of arithmetic, so it doesn't really, formally, it shouldn't actually increase your confidence in arithmetic, or maybe it should. Okay, so there's some kind of philosophical question here, right? How do we know that the natural numbers really exist? Okay, so that's sort of mind-bending question, and I have a dogmatic answer to it as well, which is that it's an axiom of set theory that the natural numbers exist. Okay, so that's the axiom of infinity. It essentially just says the natural numbers exist. Okay, so if you find that to be a compelling argument, I think you're wrong. Right, I just said, how do we know something is true? And then I told you, because it's an axiom. That's not, it's not a great argument. But it does mean that the axioms of set theory, so which are our accepted foundations for math, can prove the consistency of piano arithmetic. Okay, so that means that they're sort of formally stronger than the axioms of arithmetic, right? Because by Gödel's theorem, the axioms of arithmetic can't prove their own consistency. Okay, so ZFC, this system of axioms for set theory, is proving some very concrete, in fact, number theoretic statement that can't be proved within the axioms of number theory. And when I say it's number theoretic, what I mean is you can actually formalize the statement that the axioms of arithmetic are consistent as saying that some Diophantine equation has no solution. Okay, so this is some statement about the structure of numbers that's equivalent to the consistency of this theory. And that statement, which is true if you believe the argument I just gave, is unprovable from the axioms of arithmetic, but it is provable in this higher system, ZFC. Okay, so just adding axioms about infinite sets, like the axiom of infinity, has increased the amount that you can prove just about finite things. Non-existence of a solution to a Diophantine equation is really a property of the finite. Okay. In fact, if you take out the axiom of infinity from the axioms of set theory, you get a system which is equivalent, essentially, to piano arithmetic. It's logically equivalent or mutually interpretable, bi-interpretable, whatever. They're basically the same system. So what we've really done is we started with a system that's exactly PA, the axioms of arithmetic, and we added one axiom in, the axiom of infinity, and that was able to give us the consistency of the system we started with. Okay, so how do we know that number theory is consistent? Well, we can prove it if we add in new axioms, which seem plausible that the natural numbers exist. Okay, and why is it plausible that the natural numbers exist? I don't have this on the slide, but that's a question of philosophy. Why should we believe that there's actually an object, the set of all natural numbers? And it's basically because we have a very clear understanding of the natural numbers, and it doesn't seem like it could possibly lead to a contradiction to assume that they exist. Okay, so it gets into the realm of philosophy. If you deny the axiom of infinity, you're, I don't know, subscribing to some sort of philosophical view of mathematics where only the finite is real or something like that. Okay, so, but how do we know that ZFC is consistent? So you can try to give the same kind of dogmatic answer, right? ZFC, these are the axioms of set theory. They try to, write down a formal system which says what the properties of sets are. Okay, so why are they consistent? Well, because they hold in some structure. That's the universe of all sets. Okay, but it's almost a tautology. In some sense, you could think that the universe of sets is sort of described by the axioms, and therefore it satisfies all the axioms. Maybe it's just given by those axioms. So it's not very compelling, and also this is not a proof in ZFC, and ZFC is supposed to be the axioms for math. Okay, that's what ZFC is, or the axioms for set theory, which is supposed to be the foundational system where you build up all of math. Okay, so you could think the reason ZFC is consistent is because ZFC holds in the universe of all sets, and so if it proved a contradiction, there would be some property of sets that's true there and also false there, and that couldn't possibly happen. Okay, but that is formally not a correct argument. But you could try to do something like add in some generalization of the axiom of infinity, which would allow you to actually formalize this proof, just like we did for number theory, right? We added in the axiom of infinity, and we're able actually to prove the consistency of PA, maybe add in some generalized axiom of infinity, and prove the consistency of ZFC. Okay, the most naive way of doing this, that's the idea of large cardinals, basically, but the most naive way of doing it doesn't work, right? How do we know that V exists? This is the analog of the question before. How do we know the natural numbers exist? In a sense, we don't, right? V doesn't exist is kind of a theorem of ZFC. So that might seem like a problem. Okay. So yeah, what is the analog of the axiom of infinity for ZFC? Okay. So to describe this, we need to actually talk about versions of the universe of sets that do exist. I don't know. Normal mathematicians call them universes. Okay. So you can kind of stratify the universe of sets into a hierarchy called the cumulative hierarchy. These are indexed by infinite ordinal numbers, also finite ones, so please remember what the ordinal numbers are. The finite ones are 0, 1, 2, and 3. Okay, we're used to those. And then you can count into the infinite. So you just add in a formal symbol, omega, which stands for the first infinite counting number, or ordinal. And then omega plus 1, omega plus 2, whatever. Omega plus omega, omega plus omega plus omega. Okay, so these are kind of formal objects you can introduce. You can set up the theory of them in ZFC very satisfactorily.
So you have different degree of infinity.
Exactly, yeah. But it's different from a cardinal number, so we'll talk about those two. Okay, so you can stratify V according to the ordinals basically by starting with nothing, the empty set, and taking the power set operation, the set of all subsets, over and over, but not just finitely many times, but infinitely and transfinitely many times. Okay, so that's what this definition, which is a definition by transfinite recursion along the ordinal numbers, says. So the point of the ordinal numbers kind of is to act as stages in transfinite or infinite constructions. So we start with nothing and we keep adding the power set. And it turns out if you do this, then you can get the whole universe of sets just by taking the union. Okay, so I included some pictures. I don't know how useful they are. So you start with the empty set. Okay, this is a box with nothing in it, right? It's like curly brackets with nothing in the curly brackets. Okay, and then you take the power set of this, the set of all subsets. So the set of all subsets of the empty set. Okay, that is now above the empty set. We imagine the transfinite hierarchy going upwards. So this is a set with just the empty set in it. That's all you get. Okay, you can take the power set of that. That is just going to be all the subsets of this. So it has 2 to the 1 many elements, which is 2. Okay, every time you take a power set, you go up by an exponential, so I'm not going to get very far on this slide. So we've got these 2 elements, or the next level, kind of cool. My girlfriend said they look like mahjong tiles. Okay, so this has 4 elements, and then the next one has 16 elements, so that's V4. Okay, the next level has 66,000 elements, and then the next level above that has more elements than there are fundamental particles in the observable universe. Okay, so it gets big very fast, but we're not really concerned with these levels. We're more concerned with the infinite levels. So this is sort of the picture that we're thinking about. So at the bottom, there's the empty set, and there's these finite levels of the hierarchy. Then at this first infinite stage, omega, we take the union. So this structure is a countably infinite set, right? Because it's given by a union of finite sets. The next level, you take the power set of that. That has the same size as the set of all real numbers. You can kind of think about real analysis as existing in this level of the universe. The next level is the same as the power set, or the set of functions from the real numbers to the real numbers, arbitrary functions. So that's V omega plus 2. You could think of something like functional analysis being there. V omega plus 3 is beyond what most undergraduate mathematics textbooks ever look at. V omega plus omega, you can think about almost all of math as being in there. This is for set theorists. Okay, but still very interesting structure, and the amazing thing is how hard it is to come to an understanding of these levels. Just at V omega plus 2, you can express things like Cantor's continuum hypothesis, which seem completely hopeful to resolve. V omega plus 1, we have a pretty good understanding of the set theory there, which maybe I'll talk about at some point. Okay, so what's an inaccessible cardinal? What's the analog of the axiom of infinity for PA that we have for ZFC? So I had a quote from Gödel, which is very long and contains many footnotes. But the basic idea is that an inaccessible cardinal is just a stage of the cumulative hierarchy where ZFC holds. That's roughly the idea. Gödel said the same thing, so I don't feel that bad, roughly speaking. Anyway, so the idea is you say some stage of the cumulative hierarchy satisfies the ZFC axioms, well, then you have a natural model of ZFC. And the idea is it's just that you reached an ordinal so large that you were closed under all the operations that are basically given by the axioms. Okay, the axioms of set theory are essentially saying you can do things like take power sets and unions. And so it stands to reason that at some point, if you take enough power sets and unions, you're closed under these operations and you have a model of the axioms. You can't carry out that reasoning inside of the axioms of set theory, but you can posit that there is such a level, and given that, you have a model of all the axioms. Okay, so the axioms are consistent if you ever reach such a level. Okay. So that's the very first large cardinal axiom. It's a generalization of the axiom of infinity that asserts the existence of a very closed level of the cumulative hierarchy. Okay, but there's a giant structure here, just starting with inaccessibles and reaching into, like, I don't know, the stratosphere. So down here, this is the weakest one, and then there's a whole hierarchy of inaccessible cardinals, and then you go up, up, and up, up. Each one proves the consistency of the axioms below and is unprovable from the axioms below it. Okay, and there's, I don't know, a huge amount of detail to the structure. You can look at any part of the structure and kind of zoom in, and there's always somehow more to see if you want to see it. So this is kind of the subject matter of a lot of set theory. So how do these large cardinals interact, and how do they interact with other set theoretic principles that aren't just asserting the existence of really large numbers? And yeah, so like I said, we're focused on the very top up here. So this is, for some reason in the chart, it's traditional to write 0 is equal to 1 at the top. It's the strongest large cardinal axiom. It's just a contradiction, right? Okay, so that's the formal symbol for a contradiction. Okay, it's not a large cardinal axiom. You should not take this as an axiom. But the reason it's up there is that if you kind of keep generalizing these large cardinals in the natural way, well, there seems to be only one way up the hierarchy. You just get these larger and larger axioms in this, falling into this number line. But eventually, if you keep generalizing, you do reach a principle that's just inconsistent, sort of edge, the end of infinity. So that's what I'm going to talk about. At some point, those are the choiceless large cardinal axioms. So they're inconsistent with ZFC, and they may be consistent with just ZF. So it's some sort of, reemergence of the foundational crises of the 1910s, but for a much smaller group of people. Okay, so but here's an example of the utility of large cardinals. So it's not just proving in sort of circular ways the consistency of formal theories. What's amazing about large cardinals is that they allow us to see the consistency of just sort of basic set theoretic principles that are seemingly completely removed from large cardinal theory. So this is, one of the most basic ones. It's just part of cardinal arithmetic. So remember, Cantor has this hierarchy of cardinals: aleph 0, aleph 1, aleph 2, aleph 3. These are the infinite cardinal numbers. So they represent the equivalence classes of sets under the relation of being in one-to-one correspondence. So simplest question about them is the continuum hypothesis, right? Is the cardinality of the real numbers equal to the first uncountable cardinal number? So formally, that's 2 to the aleph 0 equals aleph 1. Right? So 2 to the aleph 0 is the size of the power set of a countable set. Aleph 0 is the size of a countable set. Okay, hope you know this. Okay, I'm sure you know this. Okay, and so it's independent of the axioms of set theory what the value is. 2 to the aleph 0 could be aleph 1, could be aleph 2, could be aleph 3. Can't be this thing aleph omega. This is the least cardinal above all the aleph n's. That's impossible. That's basically the only constraint. It's called Koenig's theorem. So there is one constraint on the size of the real numbers. Okay, but again, the values of the 2 to the aleph n's are independent of the axioms. And then you could ask, what about 2 to the aleph omega, right? So you look at this first limit ordinal. You've got aleph 0, aleph 1, aleph 2, aleph 3, aleph omega. What is the size of the power set of a set of cardinality aleph omega? Okay, it's consistent that it's aleph omega plus 1, just the next cardinal. That's just shown by exactly the method that Gödel used to show the consistency of the continuum hypothesis already shows this. But what about the question of whether 2 to the aleph omega could be bigger than aleph omega plus 1? Okay, this is a much harder question, which was open for, I don't know, 10 years at least after the proof of the independence of CH. Because it turns out to be related to large cardinal axioms. Okay, so it's a theorem of Giddick from the 80s, very early 80s, that the statement basically that 2 to the aleph omega is greater than aleph omega plus 1. So the independence of this is, the consistency of that is equivalent to the consistency of quite large cardinals, much bigger than an inaccessible cardinal. So the only way to see that this is consistent, I mean, assuming it is, which it very much seems to be, the only way to know that, or the simplest axioms from which you can prove that, are large cardinal axioms. Okay, so in set theory, we kind of come to understand whether something is consistent using large cardinal axioms, and sometimes you're forced quite high into the large cardinal hierarchy just to understand a relatively simple statement, which is not about large cardinals. It's about what to a set theorist is a very small cardinal. Okay. Do you want any comments on this? What are these extra hypotheses? I mean, the point here is you need some constraint on 2 to the aleph n to make this non-trivial, right? If I just say that the continuum is really huge, which it could be, like bigger than aleph omega plus 1, then of course 2 to the aleph omega is going to be very big. So the point is, if you constrain the cardinals below, then the value of 2 to the aleph omega becomes much more subtle. And okay, it is independent, but the only way to prove that it's independent is with large cardinals. Okay. So, yeah.
So I'm really confused.
Uh-huh.
The economist, we're doing axiom choice. That's why I came here.
Uh-huh.
Isn't this too contradictory? The first says Gödel shows that 2 to the z is constant. Then you say this is not to the z. The 2 to the power
Sorry?
a epsilon equals to a epsilon plus 1. You said this is consistent.
It's consistent, yeah.
And then you also claim
That the negation is consistent as well. Not at the same time. Separately, each one is consistent. So consistent just means that you can't refute it. Doesn't mean that it's true. Yeah, it's possible. No, it's a great question. Okay, but to know whether something is consistent requires basically to know that these strong theories are consistent. That's all this is saying. Okay, and that's kind of the point of having all these strong theories. Okay, so what are large cardinal axioms? Finally, I will tell you, sort of. It's kind of weird, the way the strong large cardinal axioms are formulated, it seems to be the only way up the hierarchy, but it's not obvious, sort of subtle. So they're given by the existence of sort of structural features of the universe of sets, these elementary embeddings. So maps from the universe of sets into some substructure of the universe of sets, M, okay, which are non-trivial and truth-preserving. Okay, this is the way to formulate strong theories in set theory. Okay. So this comes out of work of Scott in the 60s, who discovered that a large cardinal axiom, called a measurable cardinal, which was studied by Ulam in the 30s, is equivalent to the existence of such an embedding. Okay. So what is the large cardinal that's associated to this embedding? It's called the critical point. It's just the first cardinal number that's shifted by the embedding. It's moved up. Okay. So that's the critical point. So here are some examples. Not very important to read them. A measurable cardinal is just the critical point of some elementary embedding from V into some inner model. Okay. The other ones, yeah, I would not want you to try to parse them right now. But they're just saying basically that you can enlarge this submodel. And by enlarging it, you get stronger and stronger axioms. That's the pattern that was discovered, and that's how we got this giant hierarchy. Okay, so the pattern is this. The larger the model, the stronger the large cardinal hypothesis. So that basically by putting more constraints on the embedding, you push this critical point higher and higher. And you get formal theories that are stronger. Okay. So people tried to push this all the way. So you have this framework for formulating large cardinal axioms in terms of elementary embeddings. Some embedding from the universe of sets into some submodel. Okay, and the stronger, if you want to get a stronger axiom, you just make the submodel bigger. So why not make it as big as possible? Just put all of the sets into the submodel. Okay, so flew too close to the sun. So yeah, these large cardinals can't exist. They're incompatible with the axiom of choice. Okay, so they're incompatible with the ZFC axioms, which are our foundation. Those are the axioms for V. So yeah, they just aren't there. So it's a weird situation. We have this hierarchy of principles, and they seem natural, and each one seems inevitable given the previous ones. And yeah, you keep extending them, but there's sort of an end to infinity, at least in this sense. So, and it's disturbing, right? Because the principles are not obvious or intuitively clear. This embedding framework, it's not obvious that it's the right framework. And this is sort of a disturbing point, that if you take it to its ultimate conclusion, you just get something false. Okay, so it's worrying. Okay, so at some point, this framework for formulating axioms just breaks down. And people have very intensely studied the very exact point where it breaks down. It's not, in fact, it's not right here. It's something slightly more subtle. Someone gave a talk about that a few days ago. Farmer Schlutz. Okay, but, so how is it related to the axiom of choice? This is the reason you're here. Okay, so the proof uses the axiom of choice in an essential way. So it's not like every time someone uses the axiom of choice, we descend and try to see whether the thing could be proved without the axiom of choice. It's just that the large cardinal axioms for set theory are fundamental. And so if there's this conflict between another fundamental axiom for set theory, then that's important. And if you're really diehard about large cardinals, you might suggest, well, let's just drop the axiom of choice and keep going up the large cardinal hierarchy. Okay, so that's the question that Kunin asked. If you drop the axiom of choice, can you have a Reinhardt cardinal? And the thing that's strange here is it's unclear how you could possibly answer this question, because our methodology for proving consistency is to use large cardinal hypotheses. But we've reached a large cardinal hypothesis that's just false in the presence of choice. You would need to have, and it's stronger. It seems to be stronger than any large cardinal hypothesis you can formulate in the context of choice. So you're kind of stuck. So I guess the approach to this, and it's basically the approach I'm taking, but one approach was, okay, let's look very closely at the large cardinals in ZFC just up to the point where the inconsistency takes place and see if one of those is already inconsistent. So let's try to zero in on the point where inconsistency takes hold. So that's been carried out, and it seems to be, you can isolate exactly where the inconsistency is and try to analyze the axioms up to it, and they all seem okay. Okay, and I'm going to talk about trying to understand the axioms without choice. And here the issue is it's really hard to do set theory or to develop any kind of theory without any kind of transfinite set theory without the axiom of choice. The axiom of choice is like the most important principle for doing anything with set theory, especially up high. So you have to work pretty hard. But the nice thing is we have this extra axiom, and it is itself useful. Okay, so we're not just trying to develop set theory without choice, we're trying to understand some axiom that you can't understand in the presence of choice. Okay, so why should you care about Reinhardt cardinals? You can assume the axiom of choice so they don't exist. Okay, so let's be as unfair to the Reinhardt cardinals as possible. I want to argue that you should, if you're a set theorist at least, or if you're interested in large cardinals, you should still care. Because just the consistency of Reinhardt cardinals, even in the absence, so the consistency of Reinhardt cardinals without choice still has implications. Okay, so even if the axiom itself is false, it could still be consistent without choice, and that has implications for set theory with choice. Okay, so maybe confusing. So for example, these are questions about ZFC set theory, the Hod conjecture, the ultimate L conjecture, and they're just false if Reinhardt cardinals are consistent without choice. Okay, so certain programs in set theory cannot succeed if Reinhardt cardinals are consistent. So it would be useful to know if Reinhardt cardinals are consistent so that we can stop trying to prove things that are not provable. Okay, so there are ramifications for set theory with choice of the mere consistency of the formal theory ZF plus a Reinhardt cardinal. Okay, and again, these are large cardinal hypotheses. So just like, a measurable cardinal with O of kappa is kappa double plus allows you to prove the consistency of the failure of 2 to the aleph omega is aleph omega plus 1. There are formal theories consistent with choice that we can prove consistent from a Reinhardt cardinal, and we don't know any other way to prove they're consistent. Okay, so they reveal that theories are consistent, even theories in the context of choice. Okay. So if they are consistent, we should prove it from true axioms, but true or believable axioms, but we don't have any large cardinals beyond them, so how can we do it? So it's perplexing, at least. And in fact, there's a whole hierarchy of large cardinals stronger than a Reinhardt cardinal, as long as you drop choice. So there's way more than just this J from V to V. There's many embeddings from V to V. So could they possibly all be consistent? It seems like it's very appealing philosophically to try to just refute all of these things just in ZF, because then you wouldn't have to worry about these kinds of weird questions. It should be that all of consistency can be established from the large cardinal hierarchy. And if you want your foundations to be in the presence of choice, it would be useful if these things just didn't exist. They're just some illusion. Yeah. Mm-hmm.
So, the scheme of the universe was in C.
Yeah.
So if you try that sort of future, you replace V with something else to begin with.
Yeah, that's a good point. So V is supposed to be the universe of sets, and yeah, so maybe we should give it a different symbol when we're talking about some other concept of set where you're not assuming choice. Formally, V just means all of the sets, so you can study it in the context of ZFC, or you can study ZF, in which case when you refer to V, you're not assuming that all the sets satisfy choice. But yeah, so there's something.
Something like bigger than V, you don't assume.
That maybe is one way to think about it, yeah. I mean, you can imagine that you just, you started iterating the power set, you got to V omega, and then you took the power set of V omega, you got to V omega plus 1, and there simply was, some function that doesn't have a choice function at that level, some function from the reals, some collection of sets of reals that has no choice function. And then you got to v omega plus 2, and choice is just false. So you just made a mistake by assuming the axiom of choice. You were using a false axiom for v. But it's the same hierarchy of sets, you were just wrong, mistaken. Does that help a little? Maybe. Okay, so what I want to talk about, and I'm still going to use the symbol v, because it's still the union of the v alphas. It's just, we're dropping an assumption. We don't assume AC. Try to understand the v alphas if there is an elementary embedding from v to v, if there is a Reinhardt cardinal. Okay, so with choice, the v alphas, their behavior just depends on whether alpha is a limit ordinal, so like omega or omega plus omega, or a successor ordinal like 1, 2, 3, or omega plus 1, or omega plus 11, or omega plus 17. Okay, so the successors are the things that are one more than something below. With the Reinhardt cardinals, the structure of the levels of V depends instead on the parity of the index ordinal alpha. Okay, so it's a weird phenomenon. So this is the phenomenon I want to talk about. And it seems like the first structural phenomenon to understand if you're trying to get a grip on this choiceless theory of large cardinals. So what's the parity of an ordinal? I mean, okay, for the finite ordinals, it's just the usual even or odd. Okay, then we just declare that the limit ordinals are even. And then omega plus 1 is odd, omega plus 2 is even, omega plus 3 is odd. Okay, so you look at the limit ordinal below it, and you ask, is there an even or odd number of steps in between? Okay, that's how we figure out if an ordinal is even or odd. I think it's fair. Okay, so the simplest instance of periodicity was discovered by me and Farmer Schutzenberg, who was the speaker here days ago. I don't want to talk too much about this theorem. It just says that there's periodic behavior of the elementary embeddings from a level of the universe into itself. Okay, they're sort of metamathematical properties. The definability of an embedding depends on whether the level of the universe you're looking at is even or odd. So this was a sort of unusual thing because it never has shown up in set theory before that some property of the levels of V depends on their parity. It's basically, I think. Okay. And what I want to talk about are, okay, this seems like, this is just actually some property of elementary embeddings. You can dismiss it. It's not really such a property. This is something about embeddings, not about the V alphas. So I want to talk about properties that if there is a Reinhardt cardinal, really do depend on the parity of V alphas, and they're just properties of the size of the V alphas. So it's sort of like the generalized continuum problem. So how big is 2 to the alpha for every alpha? That's a generalization of the continuum hypothesis. We already talked about it. Another way to talk about the generalized continuum problem is to look at the size of the V alphas. I'll show you an equivalent form of it. Okay, but first I have to talk about what I mean by size if I don't assume the axiom of choice. Okay, remember the cardinals. This is what set theory is about. So under AC, and this is maybe the most useful thing about AC, you can assign to every set a cardinality among the alephs, right? It's some aleph alpha. And 2 sets get the same cardinal as their invariant if they're in bijection with each other. Okay, it's great. In ZF, that's just not true. You can't assign aleph numbers to sets as invariants, complete invariants for equicardinality, equinumerosity, right? Bijections. So you can't do it, so you can sort of weaken it. For each set X, let's look at the least cardinal number, such that there's no surjection from set X onto a set of cardinality theta, okay? So some sets really do have cardinality, some aleph number, some cardinal number, Okay, and we can try for any set to look at the least set that it is not surjecting onto, the least size of a set it cannot surject onto. Okay, that's this idea. So it's a weaker notion. You assign a cardinal invariant to every set, but two sets may get the same theta, even though they're not in bijection with each other. Okay, in ZFC, these thetas really do give you invariance because it's just giving you the cardinal successor of the cardinality of X, right? The least the least size of a set you can't map X onto is just the next cardinal number after the size of X. Okay, pretty obvious. Okay, and then the GCH is just equivalent under AC to the statement that the theta of each V alpha is aleph alpha plus 1. Okay, there's some off by omega indexing there, but it's not that important. It's because aleph 0 is an infinite cardinal number, but V0 is the empty set. Okay, so don't worry too much about that. Okay, so one way to look at the generalized continuum problem in ZF is to look at the thetas of the V alphas. Okay. Now, how much time do I have? 10 minutes, right? Okay, I think I'm okay. So I sort of have a planned a diversion. So let's stop talking about Reinhardt cardinals for 1 second and talk about the axiom of determinacy. So this is maybe the theory, the choiceless set theory that's been the most successful. Right? It's hard to develop theory of uncountable sets without choice. But one way to do it, I mean, you want some other axiom. And one alternative axiom to the axiom of choice is called the axiom of determinacy. Okay, so it comes from topology and descriptive set theory and economics, game theory. What it states is that if you have an infinite two-player game, perfect information, then one or the other player has a strategy that always wins, no matter what the other player does. Okay? So what's a game of perfect information, like chess or checkers? In those games, they're finite games of perfect information, right? They always have to end in finitely many steps, thanks to the ad hoc rules. So in those games, it's true, we don't need to assume any axioms that one player or the other has a strategy that always wins, right? So like in chess, there's a way to play for either white or black that always wins or achieves a draw. In the games I'm talking about, there are no draws, which is why it makes sense to say that one player or the other can always win. Okay? So there's a way to respond to moves from the other player that always succeeds. So this is in conflict with the axiom of choice, even though it sort of seems intuitive that if the game is perfect information, so there's no chance, there should be a way for one player to decide at the outset how to play that would defeat anything the other player tries to do. Maybe that's intuitive. I mean, really not so intuitive. So the way this axiom arose is that people realized in the 20s and 30s in Warsaw that the determinacy of certain games associated to sets of reals was equivalent to regularity properties of those sets, so the Baire property, or Lebesgue measurability of those sets. So if there's a winning strategy in this game, then the sets really or in some family of games, then the sets have the Baire property or are Lebesgue measurable or have all kinds of nice analytic properties. So people suggested just assuming that all games are determined. Therefore, all sets have the regularity properties. Of course, that's in conflict with the axiom of choice, because from the axiom of choice, you can build all kinds of badly behaved sets, so non-measurable or not having the Baire property or all kinds of things. So AD says the sets of reals are well behaved, but what people discovered in the 60s and 70s is that it also allows you to develop a very intricate set theory for cardinal numbers, basically below the continuum. Okay. So under AD, you can compute some of these theta numbers, even though you don't have the axiom of choice, so you don't have cardinalities for every set. Okay, so for example, the theta of the omega. Okay, so this is just a countable set. So the theta of that is aleph 1, the first uncountable cardinal. And that has nothing to do with AD. That's just because v omega is size aleph 0. The theta of a set of size aleph 0 is always aleph 1, and that's provable in ZF. What does have to do with AD is that theta of v omega plus 1 is giant. It's a strong limit cardinal. So what is a strong limit cardinal? Well, it's a limit cardinal. That's one thing, so maybe that's all you need to know about it. It's stronger than being a limit cardinal. So limit cardinal just means it's not the successor of any cardinal. Okay, strong limit cardinal means that, in fact, you can't map the power set of any smaller set onto it. Okay. And then theta of v omega plus 2 is just the successor of theta. Okay, so there's some weird pattern here. We've got these two successor cardinals, but the theta of v omega plus 1, which is really the theta of the reals, right? Those v omega plus 1 and the reals have the same cardinality, so they have the same theta. I mean, they're in bijection with each other. So they have the same theta, and this is giant. The other two are relative to the previous thetas, they're quite small. Okay. And theta of v omega plus 3 is independent. So the axiom of determinacy really gives you a theory of the reals and the things that are below the continuum, and it doesn't tell you about v omega plus 3. Okay, so you can't determine this in the theory CF plus AD, if that theory is consistent. Okay. So what do Reinhardt cardinals imply for the continuum? Sort of strangely the same pattern. Okay, so this is the main theorem I wanted to talk about. If there is a Reinhardt cardinal, then if you look up sufficiently high in the universe, if you look at the thetas of the V alphas, they depend on the parity of alpha. In particular, for alpha, an odd ordinal, the theta is a strong limit cardinal. So it's similar to how the theta of v omega plus 1 is a strong limit cardinal. In fact, the structure below this theta number is very similar to the structure below theta of v omega plus 1. And for theta even, it's not a strong limit cardinal. So if you look back here, we have this same pattern. This is an even ordinal. This is a successor cardinal, definitely not a strong limit. This is an odd ordinal. This is a strong limit cardinal. This is an even ordinal successor. Okay, so we're generalizing from a very small number of cases, but this seems sort of natural. Okay, so there are some questions here. Okay, for limit ordinals, you can actually always prove that theta v alpha is a successor cardinal. For the even ordinals here, I was unable to prove that. Okay, so if you look at a large odd ordinal, you can show that theta v alpha plus 1 is pretty small relative to theta v alpha. So v alpha plus 1 is even here. So it's pretty small, and it's actually the surjective image immediately of theta of v alpha, of the power set of theta of v alpha. Okay, so you immediately see that it's not a strong limit cardinal as soon as you get to this. Remember, the definition of strong limit cardinal is in terms of being a surjective image. But, okay, the conjecture, which I think is probably provable, is that for all sufficiently large odd ordinals, you just have that theta v alpha plus 1, this even level, is the successor of the previous one. Okay, so that would kind of generalize this picture here. This picture, basically. Okay. So let me say something about the proof. The main point is, many of these things, that you can simulate the axiom of choice. using a Reinhardt cardinal. So there are consequences of choice that actually follow from the Reinhardt cardinal. And I mean, the main thing that you think when you can prove something like that is, well, I'm going to refute Reinhardt cardinals, right? I'm going to use these consequences of choice to just simulate the proof that Reinhardt cardinals are inconsistent with ZFC, and then I will answer Kunin's question once and for all and get rid of these, crazy large cardinal axioms. But in fact, it just allows you to kind of generalize large cardinal theory from the AC context, at least once you look at sufficiently large ordinals, and it only amplifies the anti-choice consequences of Reinhardt cardinals. It doesn't lead to a contradiction. It actually just lets you develop some kind of structure. So it only leads you to think maybe they are consistent, because you can actually get some kind of grip on what picture of the universe of sets they're trying to show you. Okay, and the other aspect of this is that when you try to show that something is a strong limit cardinal, you need to analyze the power set, the set of subsets of some set of cardinality gamma. Okay, and you do that using some kind of measure theory of ordinals. So you're looking at basically probability measures on the power set of some ordinal, so they're a total measure. And the weirdest thing about them is that they only take values 0 or 1. So everything is either probability 1 or probability 0. So it's an ultrafilter. Ever think about ultrafilters? Okay, so Reinhardt cardinals give you this really kind of amazingly detailed structure of measures, and that's where all this whole theorem comes from. On the other hand, well, they make the measures behave like the ordinals themselves in some weird way. They're well ordered. Eventually, you can well order all the measures. And then on the other hand, you can analyze the embeddings from Reinhardt cardinals, these J's from V to V, in terms of measures. Basically, if you restrict the embedding to the power set of some well-ordered set, it's given by a sequence of measures. So they give you this analysis of measures, but they themselves can be analyzed in terms of measures. So it gives you some way to actually get an analysis of the large cardinals themselves. Okay, so the last thing I wanted to talk about is this analogy between AD and Reinhardt cardinals. If you look at all the aspects of the proof I just gave, they are all aspects of how you develop the theory of AD as well. So these two choiceless theories, one AD, which contradicts ZFC just at the level of V omega plus 1, and Reinhardt cardinals, which contradicts ZFC way up high by Kunin's theorem, look very similar. Okay, so one thing you can try to do is try to lift the consequences of AD to Reinhardt cardinals. That's kind of like the theorem I was talking about. So the way to develop this theory of Reinhardt cardinals is to try to just generalize everything you know about AD, and a huge amount is known about the set theory of determinacy. Another thing you can try to do, though, if you want to convince yourself these cardinals are consistent, is sort of predict consequences of AD starting with the Reinhardt cardinal. So take the things you can prove from a Reinhardt cardinal and verify that they were really consequences of AD all along. Okay, and this can give you some sense that the picture you're getting from Reinhardt's actually was consistent, because we actually know that AD is consistent relative to large cardinals. Okay, so this is kind of some scheme for trying to understand if these large cardinals, Reinhardt cardinals, really are consistent. So develop the theory by generalizing AD, and confirm the theory by confirming its predictions from this weaker theory.